Part 1 will focus on explaining what's diffraction. And then, like I said, we limit to single slit, Fraunhofer diffraction from single slit. And from there, we move towards the spreading of the beam due to diffraction and extend to rectangular aperture. All right. First, let us look at what's Huygens' Fresnel principle that we're going to use. So from Huygens' principle, you already learned that on the wavefront, every point on the wavefront becomes a source of secondary spherical wavelets. And from Fresnel's principle, you're making use of Huygens' principle so that it can then determine what would be the actual field, the electric field at a point beyond the wavefront. So in order to calculate that, they will superpose all the wavelets that were produced here and taking into account the amplitudes and the phases. So in terms of diffraction consideration then, the wavefront that emerged from the slit is considered to be a continuous array of sources of wavelets that will superpose, that will travel forward and superpose at the observation point to produce the resultant view. Though it is not exactly a fundamental physical distinction, but this property that we're using, that continuous array of sources of wavelets here, would distinguish how we treat diffraction from interference phenomenon, whereby the interfering beams were taken to originate from discrete number of sources. So what is diffraction then? Well, it is a consequence of the wave character of light actually, and it's displayed by what we see as the bending of waves around small obstacles, or if it passes through an aperture, it's the spreading of the waves. So on the topic of diffraction, we have Fraunhofer diffraction and Fresnel diffraction. Fresnel diffraction is actually a near field diffraction, and from that you get Cornu spiral and Fresnel zone plate. And then Fraunhofer diffraction is actually far field, so there's some criteria is to meet, and we will look into single slit, and then we will then progress to double slit, multiple slit, and as well as the diffraction grating. And of course, from the single slit, we extend to rectangular aperture. And later on, we'll go into in the second part, we'll go into circular aperture and talk about Rayleigh criterion. Now, when we talk about diffraction of a wave by a slit, whether the waves are in water or an electromagnetic radiation in air, like a light wave, now the passage of this wave through a slit will then produce diffraction pattern that will appear more prominent, especially when the slit size approaches that of a waveline. Like over here, you can see it is more prominent here. Here is still quite flat, quite similar to the waves that are approaching, where the slit is much larger than lambda. Here, as the slit gets smaller and smaller until it's comparable to lambda, you can see the pattern which is more prominent. Now, in fact, you also can see diffraction of ocean waves. This is a picture of ocean waves as they come in and they meet this aperture openings here, and you can see the waves diffracting. Yeah. So diffraction actually occurs for all waves. Yeah. Okay, now we talk about spreading of waves through an aperture. So this is an example of a single slit where you have a central maximum, and on the left and right side, you will see patterns. As it goes further away, it diminishes in amplitude, in irradiance. Or from a circular aperture, you have a central maximum surrounded by concentric rings of illuminance, or irradiance rather, and they also dim as you go further away. Now these are diffraction patterns from an edge. When light passes through an edge, so the transmitted light is here, but of course here is actually wavy. As you can see, some fringes here, so it shouldn't be a straight line here. And when electrons passes by an edge, for example, magnesium oxide crystal here, then you find you will also be able to observe this kind of fringes. So, in other words, edges of optical images that you see here are actually blurred. It's not an abrupt edge that you see, but it is blurred by the diffraction. So because of this, this limits the resolution of instrument. So we will consider that as well. Now, radio waves also can diffract. Well, for example, because radio waves are long wavelength, so when you compare to the mountain peak, the edge here, so the mountain peak here becomes a sharp edge when you compare to wavelength which are kilometer in length. So this wave here will then diffract and then it can reach the receiver. Of course, there's also another phenomena that will mask this role, which is scattering by the particles in troposphere, so that the wave that reaches the troposphere will be scattered, and because of scattering, then you will receive the scattered ray. Okay, now we talk about diffraction with a pattern. Now let's start with, for example, when we have a slit and we have an observation screen which is very near the slit. What are we going to observe? So this is another way to look at it. Use under geometrical optics, light travel in straight lines, so you will see a sharp edge. So this is an irradiance, so you see a sharp edge. There's no edge effects here. So in this case, observing screen is very, very close to the aperture. Now let's bring the screen further. What's going to happen? Then the image then is that it still resembles the aperture, but with some fringe effects. So as you go further and further away, of course, in this case, we are considering slit size which are comparable to the wavelength. So we still need this requirement to get the diffraction pattern. We still need a certain requirement which you'll see in the next one. So in this case, for Fresnel diffraction, which is near field, the wavefront curvature must be taken into account. And then as you go further away, bring the screen further away, then you start to see the diffraction pattern, as you can see here. So the fringe image will have, it doesn't look like that aperture anymore. And here the observing screen is actually very far away. And here the wavefront reaching the aperture is considered to be planar. Now, we would like to distinguish Fraunhofer from Fresnel diffraction. What are the conditions or property that distinguish them? So Fraunhofer, again, I repeat, is a far-field diffraction. So this is a limiting case where the light that approaches the diffracting object is considered to be plane waves. So source can be very far away. And also, the observation screen is also considered very far away. And this light also considered to be monochromatic. And the diffraction pattern, you'll find that as you move the screen relative to the aperture, but of course still far away, the pattern changes uniformly in size only. There's no distortion in the shape. But when you look at Fresnel's diffraction, which is near field, so that the screen is very near, or the sources can be near, so that the wavefront is no more a plane wavefront, but a curvature, a curved wavefront. So you must take that into consideration. And you'll find that the shape and the size of the diffraction pattern actually changes as the screen is placed at different distance from the aperture, of course not far away as well, because then you may come into this condition. So for Fraunhofer diffraction criterion here, you'll find that the distance from the aperture to the screen must be much larger than the area of the aperture divided by lambda. All right, Fresnel diffraction, which is near field, it will occur when the points, you can consider points because you want spherical waves reaches the aperture. So there's curvature, right? And if you have parallel waves impinging on the aperture, but the observation screen can be very close to the aperture. So the image will take the limiting shape of the aperture with a little bit of, with some fringe edges. Or when the wavelength of the incoming radiation is sufficiently reduced, shorter, such that the fringes, as in the Fraunhofer pattern, would disappear and the image then takes on, slowly become the limiting shape of the aperture. So, which means that this is what we're going to see here. This range here is what we're going to see. We'll go into Fraunhofer diffraction from a single slit. So when we say single slit, is usually a rectangular aperture, but the length of that rectangle is very long compared to the width. So we call it a single slit. And here we're going to take into consideration that the source should be far away so that the wave fronts that are reaching this slit should be plane. That's one criteria. And one more criteria is the observation screen has to be very far near infinity, but that will be impossible for us to view it. So what we do is we put a positive lens to focus it to the screen, and you'll find that even with the lens, the angle will not be affected. So here we will have the slit of width B, and we draw an optic axis through the center, so that below this axis here we have a distance b over 2, negative b over 2, and here will be positive b over 2. And we consider a small little elemental width here, and at a distance s from the optical axis here, this axis that we're considering, that will be distance 0, s equals 0. So the extent of this is up to positive b over 2, and this width is ds. And we consider an observation point P here, and we'll consider a line from here. We draw it straight to this point here, and another line would be this line here, which will go parallel as well, but we bring it to focus a point P by using this lens. And this lens to the screen, this would have a distance, the focal plane here will be at f distance from the lens. And the tilt of this line here, the line observation up to point P, will make angle theta. Okay, so that this ray here compared to this ray from the center of the slit would have a path difference of delta, and the wave that is coming, the illuminating light, would have a wavelength lambda, and the point of observation here is at a distance y from the center axis here. Okay, so we said that for Fraunhofer diffraction, we are going to treat it according to Huygens Fresnel principle. So we're going to divide the wavefront at the slit into intervals of width ds, and each width ds here, very small ds here, will be a source of the spherical wavelets. So we have an array of them throughout that will span the width of the slit. And the wave from each ds would then travel different paths and they will reach point P on the screen, and they may not be in phase. So they all will add up under the principle of superposition to give a resultant field. So in other words, at point P then, we will then write the differential field of that wavelet that comes from ds at a height s. So when it reaches P, we can write that as such, whereby this will be the this will tell you it's traveling wave. So exponential ikr minus omega t has a frequency omega here. Now this one here will give you the amplitude. Now this is the expression that we use for representing spherical waves, whereby the amplitude actually falls as 1 over r, where r is the distance away from the source. So, of course, if you consider irradiance, which is proportional to squaring of the electric field, then you have the inverse square law. But if you consider just the electric field amplitude, then it is proportional 1 over r. Here, r here is actually the optical path length from the interval ds to point P. That gives you r. And EL is a constant of proportionality, and this will then give you the strength of the electric field contribution coming from each slit of interval ds. Now, look at this diagram here. We're going to set a value R0, and this R0 would actually be the distance from the midpoint of the slit width to the point of observation. That's R0. That's where at S equals to 0. And any other wave that comes from height S would have an optical path length to point P given by R0 plus this difference in path. Or it can be plus or minus. If it's from the bottom, it would be minus, yeah. Now, so in that case, we rewrite the equation just now. Instead of just R, we put R0 plus delta, this delta, which is actually equals to, now, this angle is theta, small angle approximation, so we can take this to be theta, as this can be taken to be perpendicular to this line here, and it's S sine theta. And KR, R is represented by R0 plus delta. And writing it out properly, then we can lump KR0 minus omega t multiplied by exponential IK delta. So this path difference delta is much, much smaller than this distance to the screen. And in fact, in the amplitude factor here, this one can be neglected. But at the exponential factor here, it cannot be neglected because a small amount can give rise to a large number. It is very sensitive, so we cannot ignore that. So now equation 2, then we can approximate it to just EL ds R0 exponential, and this term remains there. Okay. Now from the singles, just now from the diagram, we already have delta equals to S sine theta. So then we rewrite dEp EL ds R0 amplitude is there, and we replace delta with IK. We replace that with S sine theta. And what do we have to do? We have to sum up. We consider that wavefront to be a continuous array of spherical wave source, right? So now what we do is we will have to integrate. We have to integrate, not summation, but integrate. And not that summation sign, which is over discrete sources, but this is also summation, but it's a continuous summation in that sense, yeah? So we integrate over the entire length of the slit from negative b over 2 to positive b over 2, respect to ds. So we have this term out here. This one has no s term, so it remains there. So integrating this term with respect to ds. And that will give us, okay, this term here is here. That will give us exponential ik as sine theta divided by ik sine theta, right? And we will then integrate from negative b over 2 to b2, half of b there, half b there, and writing out in full, we will have now ik sine theta, bring it out, so we have e ik b sine theta over 2 minus e minus ik b sine theta over 2 minus sine. And we will then use simplify, make it more convenient to work with the math. So we substitute half kb sine theta with a beta. Well, beta actually represents the phase difference at point P between the waves from the center to either endpoint. So from the center to either endpoints, right? So that delta then would be beta over k, which will give you b over 2 sine theta. So equation 7 then becomes, because this we replace it by half kb sine theta, so I beta minus e negative I beta, and this term here, using Euler's representation relation, we will have this term here, and you'll find that this and this cancels, that give you 2i sine beta. So therefore, we will have EL over R0 exponential IKR minus omega t. We get 2i sine beta and a b factor, put it here. Denominator is still 2i beta. Now we simplify further. So this one and this one is common, cancels off. So then we will have ELB over R0 sine beta over beta exponential IKR0 minus omega t. So it's a harmonic wave, right? And this is the amplitude that we are interested in. So this amplitude expression here is proportional to sine beta over beta. So therefore, when we talk about irradiance, we are interested in the amplitude. So irradiance at point P will be given as half epsilon 0 C E0 squared. So squaring that term will be this term squared, sine squared beta over beta squared. So this term here is actually a constant factor, and that will give you I0. Or we can rewrite this as irradiance variation on the screen then would be equal to I0 sine squared beta over beta squared. Now sine beta over beta is actually sinc beta. So this term here will describe how the irradiance vary, and on the observation screen, resulting in a diffraction pattern from a single slit. Already worked out the irradiance expression from the diffraction of a single slit that falls on the screen, and it is proportional to a function of a sine squared beta divided by beta squared. And how does it look like? Now, if you look at this expression here, this diagram here, this shows us the variance, how the intensity vary. Now, this full line here actually depict the sinc function, just the sinc function, sinc beta, which is sine beta over beta. It will be maximum at when beta is equal to 0, and it will be 0 at pi, 0 at 2 pi, oscillates, and 0 at 3 pi. But when you square it, then you have the 0 here and then a little peak here, and squaring these, it will all have positive peak. So that will give us the irradiance. So the zeros occur at all the pi, 2 pi, and also on the left-hand side. Now, when beta goes to 0, sinc beta actually goes to 1, is equal to 1. Okay, when beta goes to 0, sinc d sum goes to 1, because you're taking the limit of this sinc function is to take the limit of sine beta over beta, and that will give you 1. That will give you the central maximum. Now, where will the zeros occur? Zeros will occur when sine beta is equal to 0, and that happens when beta is equals to integer multiples of pi. So exclude when m equals to 0, because that is given by this one here then. So therefore, we will get the condition for the zeros at half kb sine theta equals to m pi, whereby m can be plus or minus 1 or plus or minus 2 and so forth. Minus is on the left side and positive on the right side in this figure here. Now, K we know is 2 pi over lambda. That is a propagation constant. So the condition for minimum irradiance for Fraunhofer diffraction pattern from this equation, that will occur when this is equal to this. So from this one here, you get K substituting 2 pi over lambda. 2 cancels, pi and pi cancels. So you will have the lambda, bring over this side, you have m lambda, and you have b sine theta. So you come to this condition. And on the screen, which is at a distance f away, which as you can see from here, so, and we're using small angle approximation. This angle is small, so sine of this angle, because we have a sine function here, will be approximated to the tangent, and that will be equals to y here, the lateral displacement here, y divided by f. So therefore, we will have then m lambda equals to b y over f. So or we have y equals to m lambda f over b. Now, m would be the mth order of the minimum irradiance, the zeros from the center. So maximum irradiance, on the other hand, occurs at theta equals to 0 or when y equals to 0. That we know for sure. What about the other maxima, the secondary maxima? So we call the central maximum the primary maximum, and the secondary maxima will then be given by, well, when you need to find the maximum value. So we look at the sinc function now, the irradiance function, which is proportional to sinc function. So we will need to differentiate that with respect to beta, and then we equate it to 0. So differentiating this expression, we will have beta, differentiate this, cosine beta, minus differentiate this, write back sine beta, divided by beta squared, and that's equal to 0. So how are we going to solve this? The solution to this will give you beta equals to tangent beta, right? Because equals to 0, so this equals to 0. So sine bring over on the right hand side, and then cosine will bring to the denominator on the right hand side. That will give you tangent beta. So to solve this equation, the intersection point will be the point where we then locate the maximum irradiance, right? So we will then draw we solve it graphically. It's easier to be done that way. So we will draw curves of y equals to beta and y equals to tangent beta, which is in the next slide. Here we have this line is actually y equals to beta, and these are all the y equals to tangent beta curves. So the point of intersection, this is excluded. Point of intersection here, here, and here would then give us the position where the sinc function is maximum. So these points here occur at 1.43 pi. So it occurs midway between the zeros, but haven't reached that asymptotic value yet. Yeah. However, most of the energy of the diffraction pattern actually falls under the central maximum, which is much larger way much larger than those secondary maximum on the right or the left side. So in other words, we can sort of say that the central maximum represents the image of the slit, whereas the edge fringes are actually due to diffraction. Now this is a sample problem. We have a slit of width B, which is illuminated by white light. So the question asks, what will be the value of B in which the first minimum for red light falls at theta equals to 15 degrees? And what is the wavelength of the light whose first diffraction maximum, this is minimum, the maximum, exclude the central maximum, falls also on 15 degrees. So in other words, the minimum of red coincide with the maximum of another colored light, right? So then what do? We first solve for B. Now for B, we have the expression B equals to B sine theta equals to m lambda. So substituting, now m is the first maximum, so order is 1. Lambda is 650 nanometer divided by sine theta, 15 degree, and then give us 2.51 micron. So in other words, we have here the first maximum here, maximum will occur at 15 degrees, that's what we are told, at a wavelength of lambda prime. So we don't know what's this value, so we want to find that. And this lambda prime will correspond to a phase difference of beta equals to, just now the first maximum actually occur at 1.43 pi. Yeah, 1.43 pi, right? We know that. So therefore, from the first maximum, which is equal to half kb sine theta, substitute k here, we get 2 pi, 2 cancels over lambda prime. So we have pi b sine theta over lambda prime. So then we substitute the values inside because b we already found out is 2.51 microns. Change into nanometer is 2510 nanometer sine 15 degree divided by beta. And that gives 454 nanometers. So that is in the near the blue region. And what is the ratio of irradiance at the central maximum to the first of the, this is another question, to the first of the secondary maxima? So in other words, we need to find the ratio of the irradiance at beta equals to 0 and at beta equals to 1.43 pi. So which means we need to find the sinc function with beta values as such. And this, we have taken it to be 1. If you remember, the p is 1. So what about this value? So substitute. So in other words, we put a reciprocal of this become beta squared over sine squared beta. Substituting this value inside, it will work out to be 21.2. So the central maximum is 21, has an irradiance of 21.2 times that of the secondary, the first secondary maximum. Okay, so it's only, or in other words, this is only 4.7% of the irradiance at the central peak. So the edge here would have this series of maxima and minima that tails off. So because of this, it brings a blurring effect to the slit because the central maximum represent the slit, and you have this blurring effect. We're going to talk about beam spreading due to diffraction. In fact, you'll find that this central maximum will spread wider when the slit becomes smaller. Interesting, isn't it? So let's do some definition here. What do we mean by beam spreading? How do we define it? Well, let's look at the delta theta between the first minima on both sides of the central maximum. So which means that it is actually from here to here. That will give us the angular spread delta theta that we are talking about. So from equation 14 earlier, which we have m lambda equals to b sine theta, And since we have the left and right, or the top and bottom, there is m spreading plus -1 to +1, which means the delta m is actually 2. So, and we also we are also considering small angle. So we then approximate that to theta. Of course, theta will be written in radians. Don't forget that. So then we will have then 2 lambda over beta is equal to delta theta. Okay, that is the angular spread that we are talking about from the 2 minima on both sides, either side of the central maximum. Now, what I would like to emphasize here is that this beam spreading is valid for rectangular aperture. For circular aperture, then the equation 12 just now, or rather, I think it's equation 16 actually. Equation 16 will be different. Okay. So looking at this diagram here, and looking at this expression for beams for the angular spread, lambda, if lambda is larger, the angle will be larger, right? Or if b is smaller, that is the slit width is smaller, delta theta also would be larger. So in other words, the spread will be wider when the slit width is smaller, or when you use a longer wavelength, that means red light compared to blue light. And you will find that this angular spread does not depend on where you put the screen. The only thing that depends, because from this diagram you see that it's growing larger, but this angle is the same. It's only the linear width. Okay, the linear dimension of this diffraction pattern will increase with the distance of the screen from the aperture. So in other words, W here you have will be equals to L delta theta, and that will be 2L lambda over B. Now here's an example. You'll find that even a collimated beam, as it travels along in space, it will have spreading due to diffraction. It will look as if it's emerging from a slit opening. Okay. Now, the quantitative example we're going to consider is you have a parallel beam of 546 nanometer, and it has a width of 0.5 mm. It propagates across the room, and from here to there, and that's 10 meters away. So the final width of the beam due to diffraction spreading then would be equals to, we're talking about the lateral width, so it's 2 multiplied by L, 10 meters, multiplied by wavelength, divided by the slit width, and that is 21. So from 0.5 mm, it becomes 21.8 mm at the wall of the room over there. We're going to then make some consideration to get the condition for far field diffraction for the validity. What are the conditions for Fraunhofer diffraction to be valid? Now we know that Fraunhofer diffraction, we said earlier on that L must be large. So we say large. So what is the minimum value? Well, we're going to say that it should be much larger than at least at the width of the beam. Okay. When the width of the beam is equal to the slit width. So by writing that, we will have 2L min divided by multiplied by lambda will be dividing by B. So L min will be equals to B squared over 2 lambda. And from here, then we can say that if it's far field, at least it should be much larger than this number here, B squared over lambda. This is just intuitively, just a general estimate. So generally, if we now B squared dimension here would be the area of the aperture, right? So in other words, we can sort of substitute that with the area of the aperture. So general criterion for far field direction is that the distance of the screen from the aperture should be much larger than the ratio of the area of the aperture over the wavelength of the illuminating light. Next, we go to diffraction from rectangular aperture. It's quite simple. Now here, if you look at this, now these are all very narrow. These are spread wider. Now the slit is like this. So over here is spread wider because it's narrower. Over here is wider, so it's less spreading. So they are more clumped together. When you have an equal B equals to A, then you see that they are all equally spaced on both directions. So this is a two-dimensional diffraction pattern. So with that, let's then just say that if an aperture has a width of A, so the irradiance will then be using the same function again, whereby in this case now instead of beta, we say alpha in corresponding to A. So sine alpha over alpha, where alpha is K over 2A sine theta. So for the 2D rectangular pattern, then the y dimension, which we were using for the slit just earlier on, which derived for that, will be ym approximate to m lambda f over b. So for the other width, we can approximate xm equals to n lambda f over a. So the irradiance over the screen will be then a product of this one and this one. In other words, the irradiance would be I0 sinc alpha squared multiplied by sinc beta, sinc squared beta, sinc squared alpha rather. Okay, so this will involve the double integration over the both dimension. Okay. Yes, we have come to the end of the lecture. So these are the learning outcomes. I think you can read on your own. If you can answer these kind of questions, you should be. That means you're able to understand what we set out to do.